Hello, everyone. Welcome to another Learn and Share session. Today we have Nils as a speaker, and welcome, Nils. And feel free to start when you want.
Okay. Yeah. Hi, I'm Niels, and so I'm going to talk about extractable witness encryption for KZG commitments, and also a little bit about efficient Laconic OT. This is joint work with Matthias and Mark. And so to start, first of all, so we want to construct extractable witness encryption for KZG commitments. For that, it is important to first ask, what even is witness encryption? And to understand witness encryption, it is instructive to first think about like normal standard public key encryption. Okay, in a normal public key encryption scheme, basically what you have is you have a key generation algorithm normally that takes some security parameters input, and it outputs a key pair, basically a public key and a secret key. And what you can then do with it is that you can encrypt some message M with the encryption algorithm with the public key, and you get a ciphertext C, and this ciphertext C can also then be decrypted using a decryption algorithm given the secret key and the message M prime. So and what does that mean? It means basically that I can now encrypt towards a public key, and whoever has the secret key can decrypt. And well, how do I know who has the secret key? Well, that's a problem for public key infrastructure stuff. But the idea of witness encryption now is slightly different, where I don't want to encrypt necessarily towards something somebody at some point generated. I want to encrypt towards a statement that may be true or false. So if I encrypt towards a true statement, then it should be possible to decrypt. And if I encrypt towards a statement that is maybe false, then hopefully it should not be able to decrypt. So the idea is basically to get rid of the key generation part and replace all of this with an NP relation. So an NP relation is basically just an efficiently checkable relation. So basically this relation R here, it consists of pairs X and W. And there's some efficient algorithm MR that basically checks if X and W are in the relation or not. You can think of this basically, for example, as an example, a circuit satisfiability problem, for example, where you say you have some program defined as a Boolean circuit, and you say this relation now is that something is in the relation if an input satisfies this Boolean circuit. So that means that there exists an input that will cause this program to at the end accept output true or whatever. And then we can define a language relative to this NP relation and say X is in the language if there exists a witness such that X and W are in the relation. This is just normal definition of like NP relations and NP languages. And the idea is now that we replace the public key with a statement, and we replace the secret key with a witness for that statement. And well, the definition of witness encryption in the sense of correctness and security is a bit counterintuitive, maybe, because it talks about two different cases. Essentially, if we have an XW in the relation, so that means X is in the language because W exists, then we can basically take a message, we can encrypt it towards the statement X, we get a ciphertext, and we can then decrypt using the witness. And we get, if everything worked correctly, we get the message back. So this means that if X is in the language, and in particular if X and W are in the relation, then correctness is preserved. So we have basically a correct encryption scheme now. If X is not in the language, then what witness encryption says is that if I have two different messages, M0 and 1, and I encrypt both of them, or I encrypt one of them towards a statement X, then the ciphertext of M0 and M1 should be computationally indistinguishable. So nobody should be able to tell whether a ciphertext they get is an encryption of M0 or M1. The thing that is a bit weird at first glance is that what this means is that security is only defined if X is not in the language. So if you have any X that is in the language, then this definition does not say that there's any kind of security. If you have a language where it's actually hard to decide if X is in the language or not, like security will usually carry over to the X is in the language as well, but this is not guaranteed from this definition alone. It's a bit counterintuitive, but that's how it's defined. Basically, correctness holds for stuff in the language, security holds if it's not in the language. Now, what we are looking at is witness encryption for specific relations. So witness encryption for like arbitrary NP relations, so basically for all of NP, exists. We know that we can construct it, but only from very strong assumptions. So we can construct it from indistinguishability obfuscation. We can also construct it from some non-standard lattice assumptions, but nothing that is like from standard assumptions and nothing that's particularly efficient. So what we looked at is whether we can get witness encryption for some useful specific relations. And what we looked at is specifically KZG commitments. Now, what KZG commitments are, I'm guessing that most people here will probably know what KZG commitments are, but I will also not go in the details of the commitment scheme. Basically, the only thing that's important for us is actually the verification equation of this commitment scheme. But just high level, what is a KZG commitment? It's a commitment scheme that allows you to commit to polynomials. It's a polynomial commitment scheme. So it has some setup that basically needs a whole bunch of these powers of tau in there. And you can commit to a polynomial over Fp, where P is basically the order of a bilinear group. So we have these three groups, G1, G2, GT, and you have a bilinear pairing. And if you have a polynomial over Fp of some bounded degree, then you can commit to it. And what you're left with is basically a very small representation of this polynomial. And with the opening algorithm, I can then create openings or proofs that show that the polynomial that I committed to evaluates to some specific value beta on a specific point alpha. And this is verified using this verification equation. Now, the idea would be that I can now define witness encryption for KZG commitments in the sense that somebody with a correct opening should be able to decrypt. Meaning we can define a relation or we can define a language where we say, okay, it's in the language is a triple of commitment, a point alpha and a value beta, if there exists an opening such that the verification equation is satisfied. Why would something like that seem useful? Well, there are many protocols that actually use KZG commitments, and it is, think of it in a way, for example, where you have a protocol, and during this protocol, at some point, somebody sends a KZG commitment to another party, and at some later point, this party asks the first party to open this KZG commitment at a specific point to a specific value, because this somehow confirms something that they claimed before. And if all of this is correct, then they, for example, will reveal a secret. But they will only reveal the secret if the opening is correct. And if we have witness encryption for KZG commitment, the idea is that we don't need to do this. We can instead just encrypt towards the statement, and whoever has an opening can just do the decryption. So this is one example of how it could be useful. The problem is that with the normal definition of witness encryption, it turns out this is not very useful. Why? Well, if we look at this verification equation, it turns out that for any triple of a commitment, alpha and beta, we can always find an opening pi that satisfies this equation, okay? Or I say we can find it. These things are hard to efficiently compute, but they exist, okay? For every triple com alpha beta that like syntactically is of the correct form, we can find, or there exists a pi that satisfies the verification equation. So in principle, a KZG commitment can be opened at any point to any value. And that's bad for our definition of witness encryption, because that means that this is a trivial language. Like everything is in the language. But if everything is in the language, as I said, security is only guaranteed for stuff that's outside of the language. So if everything is in the language, we don't need to guarantee security, which will lead to a very simple but also completely useless construction. Like I can basically give you a correct construction of a witness encryption scheme that just sends the message because the language is trivial and everything is in the language, so I don't actually need to hide anything. So this is not a good definition when working with this kind of trivial language. But we still want a witness encryption because obviously this is not actually what we want. We want that, we don't want that the ciphertext is decryptable just because the statement we encrypt towards is true. We want it to be decryptable if somebody actually knows the witness and not otherwise. And the idea here is to do something similar to, or the difference is similar to the difference between normal proof systems and proofs of knowledge. If you know about a normal proof system, in a normal proof system, you prove that some statement is true. In a proof of knowledge, you not only prove that the statement is true, but you prove that you know why it's true, that you know the witness. And how do you define that? Well, you define it via extraction. Basically, if you can create a proof for a statement in a proof of knowledge, then I can extract the witness for that statement from you. And the same idea holds for witness encryption. Basically, we define extractability in the sense that an encryption scheme, a witness encryption scheme, is extractable if there exists a PPT extractor, such if you have any PPT adversary that can distinguish encryptions of M0 and M1 with some non-negligible advantage, then the extractor can actually extract a witness W for X, also with non-negligible probability. So how would we go about constructing something like that? Well, constructing it directly is a bit hard. We actually take a step back and construct something simpler first. What we construct is not an extractable witness encryption scheme, but an extractable witness KEM. What is a KEM? A KEM is a key encapsulation mechanism, which is very similar to an encryption scheme, but it can only encrypt random short messages. The idea is basically that the KEM functionality essentially abstracts what you want from a public key encryption scheme when you want to use it for hybrid encryption. Essentially, here, it's a witness KEM. So we have an encapsulation algorithm. The encapsulation algorithm, instead of an encryption algorithm, it does not get as input a message. Instead, it only gets as input the statement, and then it outputs a ciphertext as well as a key. The key can be thought of as just a short message that is created randomly, essentially. And the ciphertext can then be decapsulated if somebody has a witness. And this decapsulation will then result in also in a key, and if everything went correctly, then the key will be the same as on the encapsulation side. And so it's very similar to encryption. The difference is that the key is not chosen by anyone. The key just falls out of the scheme. Which means we need to slightly change our definition of extractability, because it does not, as stated before, it does not apply to KEMs really, because there are no messages now. So the slightly changed definition is that a witness KEM is extractable if there still exists a PPT extractor, such that for any PPT adversary can still extract the witness if this adversary can basically distinguish between being given a ciphertext and the correct key, or the ciphertext and a uniformly random key. If you can distinguish between these two cases, then the extractor can extract a witness for the statement. With non-negligible probability. Okay, so how would we go about constructing something like that for, well, this KZG verification equation, basically. And for that, we can look at this equation and we can observe a couple of things. So on the left-hand side, we have a pairing, and this pairing is actually computable by anyone. Like, this only uses public information. The commitment and beta are part of the statement. So this is something that is actually, if we look at the definition of the encapsulation algorithm gets the statement as input. So the encapsulation algorithm can actually compute the left-hand side of this verification equation. On the right-hand side, if you want to compute it exactly as stated there, you would need the opening pi, or the proof pi, basically, to compute it like that. And so the basic idea is now, okay, maybe we can use this, that the encapsulation algorithm uses the left-hand side of the verification equation. Decapsulation algorithm uses the right-hand side of this verification equation. And the idea is super simple, actually. So we want to construct an encapsulation scheme, or a key encapsulation mechanism. So we need two algorithms. We need an encapsulation algorithm and a decapsulation algorithm. And now the encapsulation algorithm can compute this left-hand side. And the idea is, okay, we can, for example, just randomize this. So we can choose a random value and we multiply it with this left-hand side. Now, in the actual algorithm, we've taken this R and put it in the first part of the pairing. So it's actually computed in G1, but this makes no difference, right? We could also just compute it outside. It's just more efficient if we do it inside. So basically what we've done is we've taken this value that we know both parties can somehow compute, and we've multiplied with a random value. And from that, we get basically a value S in the target group. And this is essentially supposed to be our key material. It will turn out that this key material is actually not necessarily indistinguishable from random. It is hard to predict, but not necessarily indistinguishable from random. So to get around that, what we do is basically we take a random oracle and we apply it to S, and then we have a key that is indistinguishable from random. So the question is now, how can the decapsulation algorithm basically compute the same S? We can, of course, give the decapsulation algorithm R, for example, but that would be bad, because if we give them R, if we send R like in plain, then anybody who basically knows the statement and R can just compute the same key as well, so that would be bad. So we need to somehow hide the R in our ciphertext that we basically send to the decapsulation algorithm. And the idea is now, okay, so on the left-hand side, we multiplied simply by R. If we also multiplied on the right-hand side by R, we can also pull this R into the pairing, but put it on the other side. So what we can send as a ciphertext is simply R times the G2 part of the pairing on the right-hand side, which is just the tau minus the alpha. And the decapsulation algorithm can now simply pair their opening with the ciphertext, and it's easy to see that basically the S that you compute there will be the same S that the encapsulation algorithm computed. You put it again through the random oracle to get an actually uniformly distributed key, and then we can return the key. And this is basically it. So this is the full witness camp. If we want to construct a witness encryption scheme from that, then we can use this key in a symmetric encryption scheme to basically then do encryption. And we can prove via a slightly adapted standard proof for hybrid encryption that basically this gives you a full extractable witness encryption scheme. So this thing is super simple. The hard part is basically verifying that it's actually, well, actually secure, so actually extractable. And so the question is, how can we basically extract from this? And to prove extractability, we will make one assumption. The assumption that we make is the q-DLOG assumption. Basically, we say that it should be hard for any PPT adversary to reconstruct tau if they are given like powers of tau in G1 and also a bit in G2. Basically, it's like the d-log assumption, just with a bit more information. And this is the same assumption that is also used in the most well-known proof for KZG commitments. Yeah, so this is the assumption that the security will be based on. And we will prove the extractability in the combined algebraic group model and random oracle model. So the random oracle model is probably very well known. It's basically, we assume that we have some function, the function that we used here, the h. And we assume that this is a truly random function. And then if you ever want to use this stuff in reality, you then need to instantiate this hash function and hope that nothing breaks. And usually it doesn't. The algebraic group model is probably also well known, but is a bit different in the sense that it's basically an assumption on the adversary. We are assumed that our adversary is algebraic, which means that whenever the adversary outputs any group element, it needs to explain how this group element was derived algebraically, meaning using only group operations. If you look at a normal group without like a pairing, this basically means the adversary knows a bunch of group elements, and any new group element they basically need to explain as a linear combination of those group elements. And well, with the pairing, it gets a bit more complicated because you can multiply once, and but the adversary still needs to explain how they computed the value, basically. Okay, so how do we prove that this scheme is actually extractable? The idea is let A be some arbitrary, but unfortunately algebraic PPT adversary that actually can distinguish between being given the ciphertext and the real key, and the ciphertext and the random key, with some non-negligible advantage, call it epsilon. So that basically means that we have this probability that the adversary given ciphertext and KB can reconstruct B, and this probability is 1/2 plus epsilon. Okay, now let us define that K0 is actually the H of S, and K1 is the uniformly random value. And the first observation that is very important is that A will query S to the random oracle with high probability. In particular, if the advantage of the adversary is epsilon, then it will query this S to the random oracle with probability at least 2 epsilon. Now, why is that? Well, the point is basically that if they do not query the S to the random oracle, then their view will be independent of B. Okay, so we can take this probability of the adversary and we can split it up. Basically, by hit, we denote the event that S is actually queried. And then we can take these conditional probabilities and say, okay, so what's the probability that A is able to distinguish K0 from K1, given that they actually queried S? Now, if they actually queried S, well, then they should be able to distinguish between them, because in one case, they get a random value that is independent of the hash value. In the other case, they get the same value. So We can only bound the success probability by one there. On the other hand, if hit does not occur, which means that S was not queried, then we say that now the view of the adversary is actually independent of B, because as long as you do not query a value to the random oracle, the output of the random oracle on that point is just a uniformly random value. And that means unless you query it, the view of the adversary given B equals 0 and B equal 1 is identical. And therefore, in this case, the probability is actually exactly 1/2. So you end up with something like this, where so we have the probability that hit occurs, and we replace not hit with 1 minus hit, and we end up with basically 1/2 plus epsilon is equal to 1/2 plus 1/2 times the probability of hit. So we can remove the 1/2 on both sides and multiply by 2, and then we get the claim that yes, indeed, any adversary that is successful in this in distinguishing actually has a significant probability of querying this correct S. So why is that helpful? Because the adversary is algebraic. If the adversary is algebraic, that means they then need to explain to us how they computed S. And that will be helpful because we already know one representation of S, namely the one that we can compute ourselves, and then we will have two, and whether or not those are the same will allow us to either break the q-DLOG assumption or extract, essentially. So how does the extractor work? This will be first very high level, and the actual extraction we will do next. So the extractor basically receives this whole setup of the KZG commitment, because it's always necessary, as well as like a statement consisting of a commitment com and alpha and beta. And this commitment com, so even though it's just written as an input here, this commitment com is actually an output of the adversary. Like the adversary gets to choose the commitment. What that in particular means is that the adversary also needs to explain how they computed this com. Okay, now what the extractor does is basically just compute completely honestly an encapsulation. So the extractor basically chooses a uniformly random R, computes the ciphertext exactly as specified by the encapsulation algorithm, and then chooses a random K and just invokes A on the ciphertext and K. And now one might wonder, why do we not need to flip a coin and either give the correct key or the random key? The answer is that this is exactly the same thing that I argued before. Like until the point when the random oracle is actually queried on S, it makes no difference, because in both cases, the key is then a uniformly random key, unless you actually query S. And since in the next step, once S is queried, we just abort A, it makes no difference that we just choose K uniformly random, independent of any kind of bit or something like that. So basically what we do is we wait for A to query the correct S, and then we abort the adversary, and then we extract. How we do the extraction, we'll see on the next slide. And if S is never queried, well, then the extractor is out of luck. Then the extractor basically needs to just outputs an error symbol and can't do anything about it. However, the good thing is that because we argued that S will actually be queried with significant probability, we know that this doesn't happen too often. So how do we actually extract? So we use the AGM to extract, which means we use these representations of the group elements that the adversary needs to output whenever they output a group element. So when the adversary chooses the commitment, they basically need to explain this as some linear combination of these powers of tau in G1. For S, it's slightly more complicated. The reason is twofold. Once, in the meantime, the adversary has also received a ciphertext. So basically, they can also, of course, do things like combine stuff with this ciphertext to compute S. And the second thing is that S is in the target group and not in G1. So that means that before like adding stuff up, you can also do like one multiplication by using the pairing. So what we end up with here is that this green part is basically just the powers of tau. In the case of S, this goes from 0 to 2D because we can basically pair those powers of tau with themselves, and then we end up with higher powers of tau. But yeah, so these are basically the powers of tau paired with other powers of tau. The red part is just the powers of tau paired with the ciphertext. And the blue part is the ciphertext paired with itself. And for each one of those possible group elements, basically, the adversary specifies a coefficient, and then we basically get this large linear combination of all of these group elements, and this is the explanation for how S was computed. Right, so one thing to note here is that we allow the adversary here more freedom than they probably have in the real world. The reason is that if we use, which is usually done, an asymmetric pairing, in particular type 3 pairing, then a lot of these group elements here are not actually efficiently computable. So because we only have most of the powers of tau in G1, which means like you cannot pair the higher powers of tau with themselves, for example, because you don't have them in G2, so you cannot do pairing. But we just allow the adversary more freedom than they actually have, so nothing breaks in. And we can simplify this representation slightly by basically factoring out this R times tau minus alpha and putting this outside this sum. And then we're left with this simpler sum that is essentially just a linear combination of all the powers of tau. Okay, so what we can now do is we can define two polynomials. We define the polynomial f using the coefficients fi that are basically part of the explanation of the commitment cum. And we define a polynomial g, this is a bivariate polynomial, using the coefficients from the explanation of s. And if we do this, basically what we get is that if you evaluate f on tau and bring that into G1, then you basically get this. So basically this evaluated on tau in group G1 is just the commitment. And this evaluated on tau R in the target group is basically our S value. And okay, so to extract, the extractor now basically checks one thing, and it checks whether this polynomial g is equal to y times f of x minus beta. Now, this actually corresponds to how the encapsulation algorithm can compute S. And if these are the same, then the extractor outputs pi, which is just this sum, basically this middle part of the of this explanation of S. So basically this part. Okay, so if these are the same, one thing we can note about that is that this means that a bunch of these coefficients in G actually have to be 0. Why is that? Well, G needs to be the same as y times something here. which means that every monomial in G actually needs to contain Y. These up here, the Wi times Xi do not contain Y, so that means that all the Wi's need to actually be 0. The same thing back here, where we don't have a Y, we have a Y squared, which does not occur on the other side, which means that also H needs to be 0. So what we're left with is basically just this middle part as our polynomial G. We can simplify the G, therefore. So what we now want to check are essentially two things. So we want to check that this value that the extractor outputs is actually a correct opening, so that the evaluation, the verification equation basically holds for this pi. And then we want to check that this condition that these are the same is actually okay. So in the sense that if it would occur only with negligible probability, then this would not be good, right? Because then we would be able to reconstruct pi, but only with negligible probability, which would not be enough. So we need that this actually holds often enough. So let us first check that the output, if it occurs, is actually correct. So if the extractor outputs anything, basically outputs a pi, then we know that this equality holds. Now, as I said, we can simplify the definition of G because all of these coefficients need to be 0, because otherwise it could not be the same. So we can plug in the simplified definition of G, and then we can actually divide both sides by this part here. Basically, we divide by Y times X minus alpha. And on the other side, we have a Y, so that cancels out. And then we're left with that this sum of qi times x to the I is equal to f of x minus beta divided by x minus alpha. And now if we look at the output of the extractor, the output of the extractor was this. And this is just this evaluated on position tau and put into group G1. So that means now we actually have a value for the output of the extractor, and we can just plug this value into the verification equation and check if it holds or not. And well, we can just do that. So we can start with the right-hand side of the verification equation, which actually contains the pi, and we plug in this value that we now know that this pi that the extractor outputs actually is. Okay, and we see here that we have f of tau minus beta divided by tau minus alpha, and we pair that with tau minus alpha. Now, what the pairing does is basically it multiplies those two parts. So what we end up with is basically f of tau minus beta now in the target group because the pairing has been evaluated. But we can also rewrite this as pairing the same thing, but in group G1 with the generator of G2. And now we can look at, so what is f of tau? Well, if we look back to what f basically is, f is basically this. And if we evaluate it at position tau, what we end up with is simply the commitment. So we can plug that in, and what we have then is just the left-hand side of the verification equation. And therefore, that means that the verification equation actually holds if we output this proof pi. So that means if the condition is satisfied, then our output is correct. But the question remains, what is the probability that the condition is satisfied? So the extraction fails if these two polynomials are not the same. So the question is, what is the probability that these two equations, these polynomials, are not the same? And this is where we will use our computational assumption, the q-DLOG assumption. Essentially, we can define a new polynomial q as by basically subtracting the right-hand side of this inequality from the left-hand side. And what we end up with is, by definition, because these are not equal, we will end up with a polynomial that's a non-zero polynomial. However, we can, if we evaluate this polynomial at position tau and r, basically what we have is that this g of tau and r, this is just the representation of s that the adversary gave us. So that is how the adversary explained their choice of s. On the other side, if we basically evaluate this part on tau and r, what we end up with is this, which is basically just how we ourselves, so the encapsulation algorithm, or in this case, the extractor actually, computed the value s. So both of these are representations of s, which means they are the same, which means that this polynomial q is actually 0 at that point. So what we have is a non-zero polynomial with a root at position tau r. And why does that help us? Well, that helps us because it actually allows us to extract tau or r from this polynomial. And we can use that to solve the LD-log assumption. So we can rewrite q as essentially so q is a bivariate polynomial. We can rewrite it as a univariate polynomial in y with coefficients that are univariate polynomials in x. And then we can define p as the polynomial that is basically the same as q, but we fixed x to be tau. And then we have two cases. We have the case that p of y is not a zero polynomial. Well, if p is not a zero polynomial, but we know that p evaluated at position r is 0, then that means this is a non-zero polynomial with a root at position r, which means we can just factor this polynomial. We can basically find the roots of it, and one of those roots will be r, which means we can recover r from the root of p. And now if we do a reduction to the LD-log assumption, we can basically put our challenge of the D-log assumption into R and then recover it if all of this basically turns out to be true. Which means that the probability that this can be true is only negligible, because otherwise we would be able to break the LD-log assumption by recovering this. On the other hand, if this polynomial p is actually a zero polynomial, then that's interesting, because that tells us that C1, C2, and C3 must all be 0 at position tau. But we know that at least one of them is not a zero polynomial, because otherwise the whole polynomial would be a zero polynomial, which we know is not the case. So that means we have at least one non-zero polynomial here with a root at tau, which means we can again recover tau from basically by finding the roots of one of these polynomials. And then we can do a second reduction, essentially, also to the LD-log assumption, where we then embed our challenge, this time in tau, and basically recover tau from these roots, which means that also the probability that this case occurs must be negligible. So if we now look at the extractor, basically you can think of the extractor as being executed like in this tree, and they terminate whenever they hit a leaf. And the red leaves are basically when the extractor has failed to extract. The green leaf is when the extractor was successful in extracting. And the question is now, what is the actual probability that the extractor is successful? And at the beginning, we basically argued that the probability that S is actually queried, so the probability that hit occurs, is at least 2 epsilon. So the probability that not hit occurs is 1 minus 2 epsilon. And we also argued now that that one of these two cases occurs. Each of those is basically negligible because we could break the q-DLOG assumption if it were not. So that means that also the parent of these two leaves must have negligible probability of occurring, which then basically gives us that the probability that the extractor is successful is basically 2 epsilon minus something negligible. Since 2 epsilon is a non-negligible function, that means the extractor is actually successful, and therefore our scheme is actually an extractable witness encryption scheme, an extractable witness chem in the combined AGM and ROM. And as I said, you can basically then do hybrid encryption to get a full witness encryption scheme from it. Okay, so this was like the main part and the main technical part. The question is now, or could be now at least, why would I even want a witness encryption scheme for a KZG, and do we have some concrete application for it? And in the paper, we, as the title suggests, we have one specific application, which is a very efficient Laconic Oblivious Transfer protocol. So to explain that, let me take a step back and just start with what Oblivious Transfer is. So an Oblivious Transfer is basically a protocol between two parties. One of the parties, say on the left, Alice, wants to send one of two messages to Bob. So she has two messages, Bob has a bit, and they communicate, and at the end, Bob learns the message MB. Let's make it simple and say this is two-message OT. So Bob sends one message to Alice, Alice sends one message to Bob, and then he learns MB. And the intuitive security notion, the actual security notion, is much more complicated because it needs to be simulation based, and but this is not really helpful for the explanation right now. So let's say the intuitive security notion is basically that Alice should not be able to learn anything about the bit B, and Bob should not be able to learn anything about the other message, so the one that he did not receive. Now, there's a variant of Oblivious Transfer, which is called Laconic Oblivious Transfer, which was first introduced by Cho et al. And the idea is that we want to make the communication overhead of many oblivious transfers as small as possible. The idea is now, instead of running individual oblivious transfers every time you basically want to exchange a message, you say that at the beginning already, Bob has like a whole dictionary of many individual bits. And he computes his first message based on this entire dictionary. This message, the length of the message should be independent of the length of the dictionary. And he just sends this thing, which is called a digest, to Alice. And now Alice can basically take her two messages. And let's say we start numbering them. So we have two messages in the first round. She sends a message to Bob, and Bob learns the corresponding message for this first round, which depends on what the value of basically the first entry in his dictionary is. And then when we want to do a second oblivious transfer, we don't need to like send both messages. Now, what Alice can do is she can simply continue sending messages to Bob without Bob having to do anything. And also these messages should be short, in particular, independent of the size of the dictionary. And basically, you can do that for a very long time. In this case, I said the size of the dictionary is n. So basically, you would end up with being able to do n oblivious transfers using only very little communication. So how could a witness encryption scheme for KZG help in constructing something like that? Well, the idea is that basically we use the KZG commitment to compress this dictionary for our digest, and then we send the messages encrypted using statements that contradict each other. So this is basically the scheme. So we use the KZG commitment essentially as a vector commitment here. So we commit basically to this dictionary, in the sense that we use the entries of the dictionary as the coefficient of our polynomial, or the coefficient, no, not as the coefficient, at the evaluations of the polynomial. And then we basically send this as our digest. And when Alice wants to send a message, basically she encrypts M0 and M1 under two statements. And the first statement is that this commitment, that is the digest, can be opened at position I to 0, and for M1, that the commitment, that is the digest, can be opened at position I to the value 1. So these two statements essentially contradict each other in the sense that if somebody would be able to basically decrypt both of these messages, then that would mean that we can extract from them openings that correspond to both of these, which would mean we can open the same position to two different values, which would break binding of the KZG commitment scheme. The truth is that we need to use a slight modification of the KZG commitment scheme, because we need some very weak form of hiding, which the normal KZG commitment doesn't have, but it's really not that relevant here. So basically, we just encrypt toward these two contradictory statements, and because they are contradictory, only one of them is basically decryptable, and so this is how the Laconic OT then works. Right, and it turns out that this is actually very efficient. So if we look at the digest basically, this is where we essentially just the KZG commitment. So these are just 84 bytes, independent of how large our database is. The sender's message, which is basically two ciphertexts of our witness encryption scheme, are just 256 bytes. Also independent of the size of the database. And so sending and receiving is in milliseconds, so this is very efficient. Actually computing this digest for larger database sizes can take quite a while, so in the minutes, not like days, but still not that fast. The reason is basically that we need to pre-compute all of these openings, essentially because otherwise during the receiving we would be too slow according to the definition of a Laconic OT. Right, so the one major downside is that the public parameters of this scheme get very large if you get to very large sizes for the database. So can you end up with public parameters on the order of 100 gigabyte. Although one should note that like 2 to the 31, which is mainly here because we compared it to other Laconic OTs that basically had this database size. And this is a very large database size. So you can imagine, like, if I had a database of this size and I were to do 1 OT every second, then I can do that for like 68 years straight without stopping. So it's very unlikely that anybody would ever want to use such a large database size. And with reasonable database size of like 2 to the 18, like 12 megabytes is not that bad for public parameters. Yeah, so basically the public parameter, the scheme is either has much shorter messages than previously existing schemes, or is much faster. So this is a very efficient scheme and could be very practical if somebody needs a Laconic OT. With that, yeah, we're done. And if there are questions, I'm happy to answer them.
Thank you very, very much for the great presentation. So for everyone, feel free to ask questions. Yeah, you can unmute yourself and ask questions, or you can write it in the chat.
Hi, can you hear me?
Yes,
Hi,
hi,
yeah,
hi.
Yeah, I love your work and presentations. Very nice and interesting, and especially the way to construct the tree for the failure probability as the Q. And because I worked a little bit on the database, so I'm wondering. I mean, here, although the 2 power to the 18 is quite nice already, but I'm wondering if we can simply, for many KB database, actually, we can partially do them. So have you ever considering if, let's say, it's a KB database and we do this, we do this slice by slice, and then construct the proof for the final part?
So I don't think I got the question.
If we want to deal with a large database and we don't want to have a very large public parameter, and is that possible to do something like we do it we divided the database into several pieces, and then we do the small one and then construct the final proof. And I'm just wondering about the security assumption for that and parenting.
Yeah, so the problem with having several pieces of it is that works, and this in practice would probably be perfectly fine. Like according to the formal definition of a Laconic OT, that's no longer Laconic, because now the digest depends basically on the size of the database. We can do that, and then you have like much smaller public parameters, and I don't have the table here right now, but yeah, so in that case, the thing is that then the digest basically grows with the size of the database.
Yes.
But not like, which contradicts the definition of being Laconic. In practice, it would probably what you would do if you want to actually use very large database sizes.
That's true. And one more question. Have you ever considered actually use it in MPC? Because it already oblivious transfers. It's very natural to considering a more complex scenario in MPC.
I don't know what. Yes.
Maybe answer that. So hey, I'm also co-author of this work. So
hi, Mark.
Depending on which MPC type you consider, this can be interesting. So there are certain MPC protocols where you have a pre-processing phase, where they do some pre-computation, they store this data, and then during the real computation, so to speak, everything is done very quickly. So now in principle, you can use Laconic OT you can do the whole Laconic OT in the pre-processing phase. So even if it takes a bit longer, you can do this. And even if you don't know which choice bits the receiver would like to have in the end, it's not so bad, because you can pick them randomly. And then there's like standard tricks of how to transform something known as random OT to regular OT. So then the online phase would be very quick. And the message complexity would be still concretely very small. It would be like with Laconic OT, the receiver right now sends nothing. If you do this random to regular OT, then in the online phase, the receiver would need to send 1 bit, and then the sender would send back the appropriate OT response. And regarding the first question, maybe it's good to point out that, like, for the thing that you suggested with the slicing, we do have benchmarks in the paper in the implementation section.
Wow, that's nice. Thanks for answering. It's very interesting. Yeah.
Yeah, I also have a question. First of all, thank you for the presentation. I was wondering if there were like other applications that you could build starting from this witness encryption scheme, because like as I understood correctly, there must be a commitment existing first before the encryption is performed. So it seems to me that there's some sort of like interactivity required between like the one who's encrypted and the one who's supposed to decrypt. So basically, the one who's encrypted already must know the one that is gonna decrypt, and basically because this part must publish their commitment. So yeah, I was wondering like if this scheme can also be generalized beyond this Laconic OT, and if you had any
I mean, there are
example.
other applications at least you can envision. We have not like proven that it actually works, but so one thing is that you can, for example, in many protocols, you actually have this scenario where there is a KZG commitment, and at the end, basically one party asks the other to open a bunch of positions on that KZG commitment, and if all of these are opened correctly, then some secret is revealed. This is a conditional release of secrets stuff. And you can basically, for once, you can lower the number of rounds in this kind of protocol, because you can basically just send it encrypted before and just skip the part where you actually send the openings, because it doesn't matter. You don't need to see the openings. The other party can only decrypt if they actually have them. The other part is that also it gives you some notion of some weak notion, at least, of fairness, where basically after receiving the openings, you can not just stop the communication and not reveal the secret that you were supposed to reveal, because, well, you already sent it before, basically, in encrypted form. So there's some notion of fairness that can be achieved there. There's also some idea that basically you can achieve something that is very similar to, let's say, like a 2-round witness encryption for arbitrary messages, for arbitrary relations, I mean, because essentially, so if you look at how a lot of snarks work. So a lot of snarks are based on polynomial IOPs, and you instantiate those with a polynomial commitment. And basically what happens is you have this whole PIOP thing, and at the end, you basically are required to just open a bunch of positions in one or more KZG commitments. And if you have like a 2-round protocol, you can have this whole part that is the PIOP stuff in the first round, and then in the second round, you can basically encrypt towards this opening of the correct opening for these KZG commitments. And when you do that, basically the guarantee that you have is that this can only be decrypted if the statement is actually true. So you get normal witness encryption, not extractable witness encryption, but it needs 2 rounds, which is normally witness encryption. It's like a single, like one-shot thing where you send a ciphertext, and now this would be a kind of interactive thing. But there may be applications of witness encryption where you could replace it with that, and then this would be much more efficient.
Okay, very interesting. Thanks a lot for again.
Great. There are more questions. Okay, if there are no more questions, thank you very much, Nils, for the presentation, and everyone for attending. And yeah, so have a nice day.
Thank you for having me.
Bye-bye. Thank you. Bye-bye.